Our speaker today is Dr. Mostafa Elmorsi. He is the Vice President and the Northeast Structure Practice Leader at AECOM. So I will not follow exactly his bio because I know Dr. Elmorsi quite well. We were colleagues at McMaster long time ago while we were doing our graduate studies. So I believe when I was doing my PhD, Mostafa was starting his PhD, and then Dr. Yusuf also overlapped with him after that, and he went to the industry, and I think this is a good example about how a PhD holder can be very successful in industry. So I think he became one of the top engineers in the world, and so his professional experience include analysis, design of and detailing of steel concrete structures, including high-rise buildings, deep underground structures, arenas, stadiums, airport, and transit facilities. And he is also the author of several journals and conferences. And also, I have to say that Dr. Elmorsi, he has hired many of our students, so that we are very grateful for that. I know at least 3 of our students were hired by his company, and I think he is the one who hired them. And now he is joined also during this talk with a junior engineer, Mr. Moustafa El Sawy. He's one of our recent graduates. So he is located now in New York, working in AECOM. And also he gained a very good experience. So he worked on many large-scale projects, including stadiums, airport terminals, army bases, hospitals. And also I was impressed to see that not only he was doing design, but he did some tool development using customizing and enhancing BIM technology. So we are also very proud of Moustafa as one of our graduates. His master was in geostructure engineering, working on the dynamics of helical piles. So I think the way it's going to work is that Dr. Elmorsi, he will start the presentation, and this will be followed by Mostafa Sawy talking about some specific projects. Okay, so I will pass it to you now, Mostafa Elmorsi.
Thank you, Ashraf. Good afternoon, everyone. I'm glad and happy that I have this opportunity to talk to you today. As Professor Damati said, I lead the structural practice group for AECOM, the regional manager of the Northeast region. And our group consists of 45 engineers, and they are located in 3 offices in Manhattan, in Boston, and in Clifton, New Jersey. Our work really focuses on all types of buildings. So we do concrete, steel, and masonry buildings. We design stadiums, arenas, high-rise buildings, transit facilities, and we also design this type of complicated structures like what Mostafa is going to be sharing with us today. So it is something that doesn't fit bridges or buildings. So basically, as we tell our clients, we do everything except highway bridges. We do pedestrian bridges, but not highway bridges. And the reason for that is in our company, we have a bridge department, and that's the only thing they do. So we cannot do that also for them. Although lately we started working on design using AASHTO codes because we have a big project in Penn Station in Manhattan. It's the biggest train station in the city, and it's going through major expansion and renovation, and we are responsible for this work. and the station is located under highways, and the design of the station is covered by the AASHTO code. So we are also familiar with the design for highway bridges. I'm no stranger to University of Western Ontario, as Professor Damati just said. We've hired 3 bright engineers from University of Western, and hopefully we'll continue to do that. Our people is our biggest asset. So we are very selective when we do any hires. And our experience with the University of Western has been so terrific. That's why we keep coming back to University of Western to ask for resumes of the bright engineers graduating from there. Moustafa joined our group a few years ago, and he is now one of our senior staff that's responsible for the analysis and the design of, we don't put Moustafa on any job. It's only the complicated ones. The regular conventional stuff find its way to other engineers. So with that, I want Moustafa to share with you some of the interesting work that our group has done. And he personally is involved with the design of these projects. With that, I leave the floor to Moustafa.
Thank you, Moustafa. I'll just share my screen. Okay. I'm not sure if you guys see my presentation, correct?
Yes.
Okay. So before jumping into the main topic of today, we thought we would share with you one of the very challenging projects we've been working on for a while. I think almost 5 years now. And it keeps changing even after we finish most of the design stages. It's the Hospital of Special Surgery, which you can see here. It's located on the east side of Manhattan by the East River. And the unique thing about this project is that it's not built on land. It's actually, the client had to purchase air rights from the city, which is essentially a volume of air where he can occupy with structural and architectural elements. So this also provided challenges for us, as I'll talk about later, is that we were constrained to the volume of air that he purchased, and we couldn't go even inches out of this volume. So this is our structure. It consists of 12 stories and a penthouse, and it's also designed to take 4 future expansion levels. It's made up of built-up columns and trusses to ensure that it can span 100 foot across the FDR, and the highway will be functioning after this is built, and cars will be allowed to go underneath it as usual. So due to the unique limitations of this project, we don't have much space to erect our steel elements and put them together, given that we are on a highway and we are nearby to a river. So we had to think out of the box and develop methods where we could actually provide modular construction. And this picture you can see here is from a similar project, which is the Rockefeller University, which is also actually located on the east side of Manhattan by the East River. And we were following the same methodology where they would have modules constructed off-site, and then these would be placed on huge crane barges, which would be lifted onto place to ensure that we would not interrupt the FDR highway, which is one of the main highways in Manhattan. And you know that Manhattan is super busy, so it's first very expensive to interrupt the flow and to get permission from the city to block such a highway, and it would cause a lot of issues to the city. So we had to make sure that we would provide a minimum interruption to the flow of traffic. So we had to use modular construction. We would divide the first 3 floors into 3 modules, which would be constructed off-site and then carried on and placed on top of the highway. And these would be spliced together. And then after the 3 stories are complete, we are able to build up on top of the existing platform and continue all the construction until the 12th floor. So that was one of the main challenges we had. And I'll be speaking about more challenges as we go through. So here is a rendering of the, let me place this here. Okay, so here we have a rendering of our structure. This is actually the initial design we had. It spans 100 foot under the FDR, over the FDR. So the FDR traffic flows in both directions. We also had a 20-foot clear height over the FDR. We used built-up columns consisting of 4-inch plates. So these are custom columns made to specifications and to the architectural shape we required on both sides of the project or the structure. And we also had rock caissons and rock anchors, which are not shown here, which drilled through the rock to ensure that we have good lateral stability in our structure. So as usual, architecture are always our enemy when it comes to our design. They consistently change the design last minute. Even though we have been working on this for a couple of years, just recently they decided to change the shape of the Y columns. Suddenly the client doesn't like the way they used to look like. So we had to come up with this new shape, which looks like this. It's a Y column made of 4-inch plates. So this obviously changed a lot of the behavior of our structure, the rigidity in both directions of our structure. So we had to add this built-up girder, which also consists of 4-inch plates. And we also had to add horizontal diaphragms to ensure that the load will be transmitted to all our Y columns. Another challenge in this building, if I go back to this rendering, is that we had, first of all, we had very limited air space that the client bought from the city. And since in Manhattan, every square inch of space matters, the client obviously wanted to push it to the limits. So our steel framing at the bottom flange was exactly at the air right limit we had. So we didn't even have space to spray fireproofing on top of the structural elements that are exposed to the traffic. And the code requires that any structural elements that are exposed to traffic to be designed to have either fireproofing, or if you're going to deviate from the code requirements, you would have to provide enough documentation and analysis to prove that your structure can take fire loading in case of fire. Specifically that we had cars going underneath our building. So it's very probable that a car would catch fire for any reason, and then this heat or energy would be transmitted to our structure in terms of increased temperatures. So to convince the city that we didn't need fireproofing, we had to do some CFD fire analysis. We had two cases. We had the flow of traffic traveling north across the FDR. In this case, we would have the Y columns, and traffic traveling south. In this case, we would have the west columns. So we performed CFD analysis on ANSYS, I believe CFX solver, if I'm not mistaken. The several parameters we had to take into account were the ambient conditions, the direction of the wind, the temperature of the atmosphere at different times of the year. Also, a big part of the input was the type of vehicle that is prone to explosion or fire. And this was a big back and forth with the client until we reached a suitable vehicle. And corresponding to this vehicle, we would get the amount of energy or a curve of the energy with time produced by this vehicle. And after obtaining this information, we would be able to run the analysis. And basically what we need from this analysis is the temperatures along our surface of steel or columns. And based on this temperature, we would have two phenomena that would happen. Steel at elevated temperatures would experience a loss of a reduction in the steel material properties. And also there would be some thermal loading, which would be transmitted into our structure due to expansion of steel. So after producing this fire analysis and applying the modified steel properties and the loading into our finite element model, we proved to the city that our structure can withstand fire loading safely without any fireproofing. So this was a big part of the project. And our calculations were peer-reviewed by a third-party reviewer, and they showed that they were suitable and everything was good. And this was approved by the city. And then let's dig into the topic of today's talk, which is the vessel collision analysis and design of a pile-supported fender system. This was a very unique project to me, and I think to our office, because this is the first time we were actually working on this, and this was a proposal, and then we finally won it, and I think we just completed the 100% design recently, and construction is supposed to happen soon. So an outline of what I'll be going through today. I'll start by talking about introduction of why a fender system is needed, what initiated this movement or the motivation of the research to look and analyze systems under vessel collisions. I'll also touch on examples of different fender systems ranging from different sizes and different shapes. And then we'll discuss the vessel collision analysis and the different aspects we have to take into account in our analysis. Fender system design, which I think is probably the most challenging part for me, as it requires a lot of experience. Constructability aspects and details, and what we had to think about ahead of construction to make sure that we had no issues during construction. And finally, a summary. Okay, so it all happened in 1980. There is a bridge called the Sunshine Skyway Bridge, situated in Tampa Bay, Florida. It was a peaceful day. You can see the bridge had, there were actually two bridges in parallel, one for the northbound traffic and one for the southbound. And then on this specific day, the weather conditions were really bad, which caused this huge vessel, which is 35,000 tons, deadweight tonnage bulk carrier, to collide with one of the bridge piers. This collision caused excessive vibrations in the girder and in this, the deck, which caused the collapse of a span of 1,300 feet, which is approximately 400 meters. And I apologize in advance. I know you guys are used to the meter system, but in the US, we use the feet, the imperial units. I mean, the English units, sorry. So I'll try to mention both in the presentation. This collapse caused 35 lives to be lost, which was very unfortunate. And then a few years later, in 1987, you can see they demolished the old bridge. And here's the new bridge, which still stands today. And as you can see, they implemented some of the fender protection system, which I'll be discussing in the coming slides. So after this collapse, this was the first rise of these guidelines, which provided at least hints and good engineering standard practices on what to do when you're designing a bridge pier to take this vessel impact. It's called the guide specification and commentary for vessel collision design of highway bridges, developed by AASHTO. It was first published in 1991, and then later it was updated in 2009. And basically what they updated was removing most of the simplified methods. As you know, in 1991, the computational power of computers was not very advanced as today. So they included more sophisticated types of analysis and removed some of the very simplified methods of analysis. And this is adopted today for all bridges that are constructed in the United States, only if they have a channel which you can have vessels that can go underneath or ships that can go underneath. And the basic concepts of this guideline is it wants to minimize hazard to life. Risk of bridge service interruption is minimized to ensure that reduced losses and obviously reduced lives lost due to any collapse. Specifications need to be simple and unambiguous. Ingenuity of design is not restricted, so AASHTO actually allows you to use any type of analysis you prefer, given that you can actually prove that it works. And the provisions are applicable to all the United States, as I mentioned previously. Energy absorbing, okay, so I'll be touching on some of the fender protection systems that are used worldwide. This is a very common system for low impact forces, where you would provide these fender systems along the edge of a pier or along the edge of a slab where you're expecting ships to be traveling. And then going on to a higher impact force system, which is a Dolphin system. Basically, piles that are drilled into the ground and a wall system, which would redirect the vessel in case it steers off its path. And here's another view of this Dolphin fender system. And finally, a system that I think was used mainly in the past was the Cellular cofferdam system, which consists of sheet metal that is drilled into the ground. And there's an interlocking mechanism in those sheets, and then you would fill it with soil to provide it with a good solid inertia, and also to prevent these thin walls from buckling. So jumping into the vessel collision analysis, AASHTO considers this as an extreme event, which is very unlikely. So you would not need to increase or provide any load factors. The load factor is 1.0. There are several methods to absorb this force. You can design your system as a sacrificial system or a non-sacrificial system. From the wording, sacrificial means that after the collision happens, the system would not be usable anymore, so it would have to be replaced. So the behavior we're expecting here is inelastic behavior. And for a non-sacrificial system, you would want the system to be still usable after the collision. So you'd have to ensure that the behavior is elastic, and this approach is very expensive and very rarely used. And then finally, the simplest approach is to actually design the bridge pier itself to take this collision. And obviously you don't want the bridge to collapse, so you would have to ensure that the behavior is elastic. And then going into the numbers and details. So the way to determine this force and energy, it's based on several parameters, and big part of this is the risk and geometric probabilistic analysis, which I'll be touching on later, but it's also a function of the vessel parameters. So how much you're expecting the vessel to weigh, how much is it carrying, the cargo capacity, the dimensions, and the speed of the vessel. You're also considering the channel parameters, the flow of the river, the speed of the river, the channel width, and most importantly, the bridge parameters, how important this bridge is. So this is similar to the importance factor in conventional design. Obviously, if a structure is more important, you would multiply the forces by a higher factor to reflect this importance. So here's our bridge. You can see the bridge deck is supported on several piers. And here along this center line is the path of the vessel. And as I'll mention in the next slides, because the vessel is navigating in this path, the probability of the vessel to hit these piers is very low. It's most likely going to hit these two piers. That's why, based on the probabilistic analysis, we determined that we only need a fender system for these two piers, which are the closest ones to the channel. So you should also consider different impact angles, and obviously the sharper the impact angle, the less likely it's going to occur. Which leads to less force demand that you need to consider in your analysis, or energy demand, essentially. Also, this is a chart from AASHTO, which shows that as you move further from the center line of the vessel movement, your velocity decreases, which makes sense. And velocity is directly proportional to energy. So as the velocity decreases, the energy decreases. So just to give you an example of the type of energy or the type of impact we're expecting, at least for this specific design. For the collision shown in the red, which is a head-on collision with an angular deviation of 0, this requires 44,000 kip-foot of energy, which I know sometimes it's hard to have a feel of this number. But another way to think of it is that this is equivalent to, let's say, a typical sedan car, which weighs 1,350 kilograms. Traveling at approximately 330 meters per second, which is equivalent to the speed of sound. So this is a huge amount of energy that you need to absorb in your system. Okay, so the start of this analysis, you have to take it, always my approach to big complicated problems is to take it piece by piece. So starting from a very simple problem and advancing to the full model. So starting with the behavior of a single pile, And then after we understand the behavior of a single pile, we can go and model our whole fender system. So there are two approaches to doing this. In the academia, mostly the continuum approach is mainly used, where you would model the soil and pile as solid elements, or the pile can be modeled as shell elements. Unfortunately, this method requires a lot of calibration and sophisticated soil models, and also requires a lot of computational time. It is obviously more accurate, but you don't need this level of accuracy in the industry. So the next approach was utilizing experimental PY curves, which are lateral curves. Essentially, this is representing the soil as a nonlinear spring, which is also another term is a beam and Winkler foundation for people who are familiar with geotechnical theories. And this is mainly used in the LPILE software by Nsoft. So we ran our first initial run on LPILE. We had our soil parameters from the geotech engineers. We would push laterally the pile and obtain the force deflection curve at the pile head. And then we need to calculate the energy, because the approach we were taking is designing the system to absorb specific energy instead of doing the dynamic analysis. We were going to do pseudo-static analysis, but ensuring that we would absorb enough energy. So energy is the area under the curve, under the force deflection curve. So after you get your force deflection curve for different piers, we had 2 piers, so they had slightly different soil conditions. We would integrate this curve and get the area under this curve. And then we would have another curve which shows the energy absorbed with deflection. So after understanding this, after understanding the single pile behavior, we had to look at different aspects and what is the mechanism that this pile absorbs the energy. So by looking at the bending moment diagram, we noticed that we obviously need a ductile pile. So this eliminated the use of concrete piles. So our best option was using a steel hollow pipe section to get enough ductility. But again, nothing is perfect. So using steel, you would have other issues that concrete doesn't face. Excuse me. So our absorbing mechanism was in terms of 2 plastic hinges forming, one at the top of the pile and one at approximately 115 feet in the soil. And here we have our soil layers. We had different types of soil. Nothing special, nothing problematic, according to the geotech. And it was very vital for us to ensure that we would get our full ductile behavior and not have any other mode of failure happen before these hinges form. But as you know that LPILE has certain limitations, which is very important when you're working with any software. You always have to, there's a very famous saying, which tells you garbage in equal garbage out. If you're using a software and you don't know the limitations of the software, it's of no use. A software is only a calculator for you. If you don't know what you're punching in and you're getting answers, it's never going to work. So we knew that LPILE considers only P delta effects, and it doesn't consider any global buckling or local buckling behavior. So we knew that we had to move to a more sophisticated type of analysis, which we used ANSYS APDL, which is the old style of ANSYS, where you enter commands and you don't have an interface, or the interface is essentially very basic. We looked at the pile without any soil, just as a cantilever, just to understand the behavior of the pile section itself. We looked at the pile under different axial loads to determine the global behavior, which is global buckling. The orange curve here you can see is the pile under no axial load. It shows very nice behavior. It starts to yield and then it's almost perfectly inelastic. For the pile with the compression load, you see that as soon as it starts to yield, it actually starts to buckle. So the capacity decreases with time, which results in less energy. And for the tension pile, we have actually better performance than the performance with no axial load. So that was the behavior for global buckling. Then we also looked at local buckling. So a dirty way to do this is to have 2 models. One model will be using frame elements, which are unable to capture local buckling, while shell elements can capture local buckling. So we had the identical model, one with frame elements, one with shell elements, and we would apply lateral load. And as you can see here, up to a displacement of 7.5 feet, it almost had identical behavior. And then you would see that as the local buckling starts to occur, the energy or the capacity of the pile would start to decrease. So this, we also had to ensure that this would not occur in our structure, which brings us to the next point. Usually the codes don't require you to do sophisticated analysis to determine if local buckling occurs or not. There's a lot of research out there that provides slenderness ratio, which is the diameter to thickness ratio. And the code specifies that if you are under this slenderness ratio, you would not need to consider local buckling in your analysis. So our next step was to determine the required thickness for our piles to ensure that our slenderness ratio was below the requirement from AASHTO or any other code. And almost all codes have the same requirements because it's based on the same research. Another issue we had here is that when you're calculating the diameter over thickness ratio, the thickness you are using had to be the final thickness or the worst case thickness. And since we're used to having structures above water, we never face corrosion, or we never take it into account since stuff is usually painted or protected from corrosion. So here, even though that piles are obviously painted to protect from corrosion, you still have to consider corrosion in your analysis. So we were provided corrosion thicknesses from the corrosion experts we were working with. They provided different corrosions based on the conditions you had. So typically for piles submerged in water, you would have an FRP jacket for the first few feet, which is usually to protect the surface from wave action and deterioration of the steel. And then you would have a portion that's in water, and then a third portion that's in water and soil. So the corrosion rate changes based on the different weathering conditions. So these are where the corrosion values we were given by the corrosion experts. For the first portion, which is inside the FRP jacket, we had 0 corrosion inside and outside. For the part that's submerged in the water, we had 0.03 inches inside and 0.075 outside. And then for the part that's buried in soil, we had 0.03 inside and outside. And the reason that the part that's buried in soil is less than the part that's submerged in water is that corrosion is directly related to the oxygen available. So as in soil, the oxygen available is less than in water, so that's why we get less corrosion. And this is the total amount of corrosion we had to consider in our analysis. So the code provided limits based, slenderness ratio limits based on if your section is filled with concrete. Obviously, if it's filled with concrete, this concrete provides bracing to the walls, so the requirements won't be as stringent. It also provides special requirements for locations where you would expect plastic hinges to be formed. So we had to take into account all of these limitations, and these are the thicknesses we reached. We had a varying thickness along the height of the pile. So after understanding the single behavior of your pile, we can now move on to the global behavior for our system. So here's a plan view of our system. Our pile cap fender system consisted of 12 steel piles. Each pile was 4 feet in diameter. And the thickness varies from 1.5 inch to 1.85 inches. Here's the pier that we were trying to protect. And we tried several times back and forth with the bridge engineers to make this as small as possible so we can get enough clearance to allow for more energy absorption. So it's back and forth, and this is as small as we can get them to reach. Our fender system was approximately 45 meters by 31 meters in dimension. And we also had to ensure that we had to reduce the P delta effects since we were considering large displacements of the system, so which pushed us into this option of using hollow cast pre-sections. We would have a 12-foot by 12-foot section with a thicker front wall than the back wall. And this is thicker because this is where the vessel would impact. So the front wall was 2.5 feet thick and the back wall was 1.5 feet thick. So here's a snapshot of our full model. This is done on ANSYS, as I mentioned previously. Everything was modeled using beam elements. So the piles were modeled using beam elements, beam 188, for people who are familiar with ANSYS. The model considers a lot of nonlinearity. Here are some of the stuff that it considers: full nonlinear stress strain behavior of the curve, P delta effects, including small P delta effects, pile soil interaction, since we had our soil modeled as nonlinear springs, and also global buckling effects. Soil is modeled using nonlinear springs, the combined 39 element. Also a big challenge here, which is also fun for me, is how to connect software together. So we had to develop a script to read the LPile output text files and convert these springs to ANSYS. And you have to keep in mind that each of these piles is approximately 190 feet, and you would have a spring at every 1 foot, obviously in the part which is buried in sand. And the spring was a full nonlinear curve with different points, and every spring was different because soil behaves differently as you go deeper. And initially we placed stiff supports at the bottom because we were not expecting the piles to exceed the vertical axial capacity. But later on, we noticed that the reactions we were getting at the bottom here exceeded the pile capacities. So we had to replace the vertical support with springs. And this meant that the piles moved laterally and also moved vertically. So we're getting full 3D movement in every direction. So this was one of the biggest challenges we actually discovered maybe 2 months into the project. Here on the left, I have the continuum approach. And on the right, we have the beam on Winkler foundation approach, where we would model the soil as springs. So if you apply lateral load, 1D loading, everything looks good. You would get pressures in the continuum approach. You would get pressures from the soil in the form of contact stresses based on the interaction between these elements. While on the other approach, you would get just reactions from your spring. And the spring always applies, or the spring only, because the spring is a unidirectional element, it only feels displacement along its axis. So comes the issue when we have inclined loads. So continuum approach, everything's good. Your contact stresses always adjust based on your pile movement, so there's no issue here. But for the beam on Winkler foundation approach, it doesn't work anymore because your spring initially is like this, and then now the force is in this way. So we had to find a way to always move our spring to make sure that the spring would be always parallel to our movement. And keep in mind that we had a full pile cap, so it was rotating around the center of rotation, specific center of rotation. So each pile was moving in a tangent to the specific circle. So it wasn't a matter of fact of just making all the springs in one direction, which can be seen here. So we would determine before the start of analysis based on the loading we have. We had to consider different load cases. We would determine the center of rotation, which is basically the same idea when, if you guys are familiar with when you have a bolted connection, bolted group, and you need to determine the center of rotation for the bolt group under moment. Same idea exactly. You would get your center of rotation, and then you would draw circles to each pile, and then obtain the tangent to this center, and this is where your spring has to be placed. But another issue we have is that these springs are not, the center of rotation is not constant. As these piles start to laterally shift, certain springs at different levels start to yield. So the stiffness of the system essentially changes as the load increases. So we had to think out of the box, took a whole week of coding and thinking of how to work with the limitations we have of the structure analysis software we have. So this is the workflow we developed. So starting from initially, I'll go through it all, even though I mentioned some parts previously. Sorry. So we would start with the soil and we would start with our soil and pile properties. This would be input into LPile, and then LPile would spit out the nonlinear PY curves at different depths. And then using a script, we would input this into ANSYS and convert them into nonlinear springs. And then we would pick our load. We always tried to make our code parametric, so that we would, as the project advanced and we went into more detailed stages of analysis, we would be able to accommodate changes in geometry, changes in loading, changes in parameters we assumed at the start. So this was very important in this project. So we had load cases as one of the input parameters. And then this would automate the full fender system. And then inside the code, we would calculate the instant elastic center of rotation, and then align the springs for each pile depending on its location. And then we would basically do what nonlinear software usually do. When you're solving anything nonlinear, you're always solving in pieces of increments, because your curve is not linear. So you have to, in order to capture the changing slope of stiffness or whatever you're solving, you have to solve it in small increments. So we applied manually 5% of the load. After the application of 5% of the load, we would look at we would look at the springs and check if any of them yielded, and then recalculate our center of rotation, and then fix our geometry, adjust our springs, making sure that the stresses in all our structure is locked, and then reapply 5% of our load again, and then repeat the process until we reach 100% of the load. And then this is our analysis. So we had to take into account 2 loading cases, which is also very unique to this project. In typical structures, your stiffness of your structure does not change with time. But in our case, since we had corrosion, so as time passed, these piles would get thinner and thinner. So the stiffness would decrease. So the behavior of the structure essentially changes. So you have to think of a lower bound and upper bound approach. Sorry about the notification. Scenario 1 is where the pile cap is supported on very stiff piles. This is assuming that the piles did not corrode, and the pile's material strength is taken as the upper boundary strength. And this is very important, and specifically in this project, because when you go to a steel manufacturer, and you order, let's say, a specific grade of steel, 50 KSI steel, this 50 KSI is the minimum requirement for the members to come in. This does not guarantee that all your members or all your structural elements will come in 50 KSI. This is just a minimum boundary. So actually, in a lot of cases, the manufacturer always targets a higher number to ensure that none of his samples would fail if it's subjected to testing. So we had to assume that the piles came at the maximum upper boundary strength of the material. And this case would be used to design our pile cap, because this provided the maximum straining actors in our fender system pile cap. And scenario 2, which is used to check the clearance, which is based on the pile cap supported on very weak piles. So here we assume that the piles are fully corroded, and the pile material strength is taken as the lower boundary strength. So we had a total of 6 load cases, and then for every load case, we had 2 scenarios, scenario 1 and scenario 2. So we had a total of 12 load cases to look at. And the load combination per AASHTO was under the extreme loading extreme event scenario. You would only consider dead load, but you would increase it by 25%. And as I mentioned previously, you would not factor up your vessel impact. The loading stages we performed were the first stage, we would apply just own weight of our structure, initialize the stresses in our structure due to own weight. And then we will apply pushover analysis in the direction of the impact of our vessel. And then the output of this analysis would be a force deflection curve. It was a displacement control analysis, but as many of you know, you can actually obtain the reaction of the displacement applied. So basically the force required to perform this displacement. And then by integrating the area under this force displacement curve, you would get your energy displacement curve. And then for a specific load case and certain impact angle, we know the energy because we calculated it previously. We would see the energy deflection curve. And then, for example, in this case, we're looking at 44,000 kip foot. We know that we need approximately 17 foot of displacement. And then after we know how much displacement we need, we would look at the deform shape at the specific displacement where we have enough energy. And we had to make sure that we are not touching the pier, essentially, because we couldn't pass any load of the vessel impact to the pier, because it's not designed to take this impact. And in some cases, we had, you guys can still hear me, right? Because I keep getting messages. Okay. Sorry, I thought I disconnected. Okay. And then also a big constraint in sizing the fender system was we couldn't go as big as we want, because we had to also make sure that because we had a fender system here and fender system here, we had to make sure that there's enough space for the ship to move. And obviously making this bigger increases the cost to the contractor. So we had to make sure that we were at as close as possible after the impact. So I think in the worst case, in case 2, we had a clearance of almost 2 foot, or even here we had 1.5 foot, which is tiny, as you can see here, but still worked. Coming to the fender system design, which, as you can see, our fender system, fender cap was subjected to all types of straining actions possible. Anything you studied in your undergrad, axial, moment, torsion, shear, everything was there. We had axial compression and tension. We had moments around the 2 axes. We had biaxial flexure. We also had torsion, and we had shear in both directions, which was very challenging to design. But we have a couple of smart guys in our office, which I learned a lot from them, which helped in this design. Going back to AASHTO, we tried to follow AASHTO guidelines at the start. AASHTO provides guidelines for biaxial flexures, as you can see from here, which is typically used for simple buildings or simple design. But we noticed that this biaxial flexure relation is very conservative and has several limitations. At the same time, we had no commercial software available that can design for all of the straining actions occurring simultaneously. We kept looking if anything is available, but nothing was available that can do all of the straining actions you saw happening at the same time. So we dig deeper into the AASHTO, and AASHTO actually allows you to design using your own method, which is based on equilibrium and strain capability, which is what we ended up doing, and we had to develop our own Excel sheet programs to do this, which I'll touch on later. The strain limits we took into account were 0.003 for concrete crushing and 0.02 for steel yielding. We could have taken a higher value for concrete crushing because our concrete was confined, but we found this to be good enough and conservative, which is good, which is always good. And the tensile strength of concrete is neglected, so we assume that as soon as there's any tensile stress on concrete, it's cracked. We also, since we had full control over the program we were developing, or the Excel sheet, we input the full stress strain curve of concrete and also the stress strain curve for steel. For steel, we assumed something simple, linearly elastic, and then fully inelastic, so a bilinear relationship. And here's the methodology we applied. Just before diving into these steps, typically, if you have one direction of flexure around one axis, you would have your compression zone, which is going to be a perfect rectangle. But since here, and your neutral axis would be along the x-axis, but since we had biaxial flexure here, your neutral axis would no longer be plane, would no longer be along the x-axis, it would be actually inclined. And this is super hard to do by hand, so we had to develop this Excel sheet. And the idea behind this Excel sheet is very close to what finite element software actually does. We divided our concrete section into 1 inch by 1 inch cells, so small cells where we'd actually be able to get the stress and strain and forces on these cells independently. We applied strains at the corners to be to the limits, and then based on because we assume that everything is the strain is linear. So if you know the stress at the limits, you'd be able to get this, the strain at the limits, we'd be able to get the strain at any location. After every iteration, we would check the strain in the concrete and rebar based on stress compatibility. Stress in steel and concrete is then determined from the stress strain curve I showed previously. Knowing the strain, you can get the stress. And then obviously knowing the stress, you can get the force since you have the stress and area. And then based on the distribution of the forces, we can get the moment around our neutral axis and then compare this moment and forces or axial force with the applied external force. And we would keep adjusting the strains at the limits, at the corners, until we reach equilibrium. And this equilibrium means that the assumed strains and stresses is equal to the external forces, which implies that everything is stable. So here's just a quick snapshot of our software. Obviously, huge help from there's a Russian engineer we have, super smart guy, who I'm learning a lot from. He mainly develops and helps on these spreadsheets. So here's a stress strain curve. A strain curve. You can see since we have a hollow section, this is a strain of 0, and then we have compression here and tension here. And also it's slightly inclined to this corner since we have biaxial flexure. And also the stresses in the concrete here, they are 0 since this is under tension. And then here we have compression stresses in our concrete. So the software allowed you to input the coordinates of the rebar you had, and you would enter the coordinates of your concrete section. And since we had flexibility and control over the software you're using, we were able to actually get the stresses in each rebar individually, which will be very useful when we design for torsion, as I'll talk about later. So here's just a small snapshot of the Excel sheet. This is, I think, 200 or more rows, and it's took a lot of effort from us, but we did it. So we knocked out the axial and biaxial flexure. We had torsion and shear left. We had shear in both directions. So torsion and shear are a lot easier, even though I was told I remember in my undergrad, I was told that whenever you design anything and you see any torsion on your beam or your structure, you should know that there's something wrong. But since this is a very unique structure, we had to expect torsion. And the torsion was mainly developed due to the pile fixity. And so the pile comes in, the pile goes through the pile cap, and the pile has a restraining moment. So it will apply torsion on your pile cap. So again, we developed our own Excel sheet for this. And due to torsion, we get shear flow, but we also get an axial component due to torsion. And usually what people do when you design for torsion, you would get this axial component and then just add the reinforcement equivalent to the required axial force. But since in this case, we know exactly the rebar stresses and we know how much the rebars still have in the tank to reach yield, we were able to utilize the rebars already existing for torsion without adding any extra reinforcement. So this was certainly a very big cost saver for us. So some of the special considerations we had to think about, which we kept figuring out as we kept diving deeper and more details. We had to make sure that at the location where the pile is inserted into the pile cap, we would not get any shear failure, since we could not put stirrups on top of the pile because it's going through the pile cap. So we drew 45-degree shear failure planes, and we had to make sure we had enough stirrups along these shear planes to develop our shear capacity, which resulted in a more dense area of stirrups around our piles. Another consideration we had to take into account was we had to make sure that when the vessel impacts our pile cap, it doesn't just tear through it and just go through it straight into the pier, because then all our analysis is based on nothing. we had to make sure that when the vessel impacts the pier, we had enough capacity in our facing wall to distribute this load, essentially like a two-way system. So we had to use the yield line theory based on the UFC guidelines. This is the Army Corps guidelines. They're available online, or essentially the yield line theory is explained in any concrete book. Without going into details, you would divide your wall into panels based on the load and the expected shear lines you're getting, or yield lines. And then you would do the equilibrium for each panel. And then we were basing all our analysis based on the pile is fixed into the pile cap. Checking the time. So I'm going to try to speed up because I think we're going out of time.
Moustafa, we would like to give some time for questions.
Yeah, okay. I'll give me 2 more minutes. I'll just speed through this. So essentially here we were checking, it's similar to a big bolt. We're checking that the pile doesn't tear through the cap. Here we were checking if the pile does not tear vertically through the pile cap. So we had to check this also. And in any, we also had to make sure that the bent reinforcement would not tear out, because as you have tension, these bars tend to want to straighten themselves. So they would try to tear out from here. So we had to add hairpins to provide lateral restraint for these reinforcements. And then finally, the construction, these come in modules. So these precast come in pieces, and then they would be placed on your piles. And then we would fill the piles with concrete, and then it's good. So here is just a schematic. We would have a pile cap here. It would be placed on the pile, and then the other piece comes here, and then you would fill with concrete. And here is where we would couple them. The couplers, this was a big price item. So we had couplers for all the rebars, and each coupler cost $99. So I think it was a big chunk. And each fender system cost $5 million. And we had 2 details for the coupler splice, double couplers and single couplers. And the summary, I think we can skip. Okay, I'm sorry I went over the time.
Okay, thank you, Moustafa. You are doing advertisement for Trump on election day now.
Yeah.
So we brought Americans on election day here. Okay, so we'll try to take some questions. Personally, I have a general question I'd like to ask Mustafa Elmorsi about. And this question, I want you to elaborate about the advantage, or if there is a benefit of doing graduate studies when you hire engineers. Do you think that doing a master or PhD, that something is beneficial, that distinguishes the engineer? Or what is your comment about that, Mustafa? I think you hired.
I think it's more and more the masters is becoming a must. It is the market is very competitive now, and we see very strong resumes, and you'd be amazed at like the resumes that we get. I mean, you see candidates like with more than 1 master degree, with expertise in many subjects. So I think in this market, the masters is becoming like the bachelor of my generation. Okay. I also find that in order to get a good opportunity, you shouldn't end really at the master's level. You should also have the advantage of knowing the softwares that the industry is using. So when I get a resume of someone from a very good school with a master's degree, but he doesn't know the softwares that other candidates have, I think about it in terms of money. So somebody who knows ETABS and SAP and SAFE and Revit, for me, this is like a hot cake. I'm not gonna invest in teaching him. In the past, we used to get the engineers out of school and arrange seminars and teaching lessons to those engineers to get them up to date with these softwares. And that was costing money. But if I get someone who already knows those softwares and has a master, that's definitely a plus. As far as PhD is concerned, we have a big number of PhDs in the group. They used to make, and they are still making jokes about that in the office. In the business line, they say the structural group has more PhDs than the hospital at the corner, okay? And I see this very helpful because we are able to attract work from other groups because of what we offer that they cannot offer. AECO is a big company and it has branches all over the US and outside the US. And we attract the work from the other regions and outside the US, but by what we can offer. So if we didn't have like these PhD candidates, we wouldn't have been able to deliver this work. A lot of the work that we get it in problematic stages, like in construction, they find a problem, they cannot solve it. They come to us. Something very special like this like the design fee for this Fender system is close to $1 million. So that kept like MJ and a couple of other engineers working for quite some time. So I'm always keen on hiring this top caliber. So I would say, to summarize it, a master's becoming like a must. A PhD is something great to have.
Okay, very good. Thank you, Mustafa.
Yeah. And on top of that, the softwares, I cannot stress more on that. Softwares is very important.
Yeah, I think this presentation was very nice, Mustafa, because it elaborates many things. Like it elaborates the need of fundamental mechanics, understanding, elaborate of the design, understanding of engineering, software, and even programming.
Yeah,
so all that was included in this nice engineering project. If you have questions, please put it on the chat.
I see a very interesting question. Someone was asking, why not design the pier for this load? And that was like the initial thinking. Why not design the bridge pier for this load? But as we see here, I mean, we designed the Fender system for a lower load because we said, okay, we're going to get the system to go through nonlinear stage. So the amount of energy absorbed can be taken by lower load and more deformations. And this thing was moving a couple of feet. The bridge, the pier of the bridge, we cannot allow it to move a couple of feet. So the movement is sensitive. So it would have been designed for the full elastic load with very minimal movement. In addition to that, this Fender system, they are expecting under a huge collision that damage is going to happen to it and it's going to be replaced. And when they are doing that, they are not stopping the use of the bridge. But if the pier of the bridge get damaged, you cannot use the bridge. It's a very sensitive bridge, and the traffic cannot just be stopped because a vessel hit the bridge.
I have one technical question. I have a few technical questions, but maybe I can put one of them only. Mustafa, when you talked about torsion, it was good that you mentioned that it reduces axial load, because many people don't know that. And the reason for that, because warping. And when you prevent warping, you introduce those axial stresses. But in this case, were you preventing warping? My feeling about those collision devices, the way they are done, they will be free to warp during the torsion. And if they are free to warp, then you don't develop those axial forces.
So the issue is that so the piles are fixed to the pile cap. So the piles are essentially like a moment spring on the pile cap.
Okay.
So if the vessel collision happens between two piles, this portion is trying to warp. But you have on the supports, you have these piles providing reaction moment reaction. So we actually had a issue about this point, is that the torsion we were getting was huge. So we had to assume that it was a cracked section to reduce our torsion by half. So we did allow actually for some cracking due to torsion and the release of this torsion stress due to warping, as you said. So we didn't design for the full torsion force.
Okay.
Sorry, Ashraf, can I ask a question?
Yeah, sure. Please go ahead, Mike.
So I cannot leave my friend Mostafa Elmorsi and our alumni, Mostafa Sawy, without questions. So I have many questions, but I'll ask a quick one, quick two, let's say. The first one regarding the girder and the effect of fire on the girder. Very interesting work. And I work in fire area and I have some knowledge in this area. So when you studied the effect of fire on the girder, you mainly looked at the steel strengths. But it's well known in steel structures that thermal deformations are mainly the cause for failure and problems during fire. So did you consider this in the analysis or not?
Do you want to answer, or Mustafa, you'll answer?
We're going to allow Professor Yusuf only one question. And yes, we did consider that thermal effect on the design. And one thing we notice is the effect of this thermal stresses on the connections. This building, the way that the connections are designed, they were designed exactly for the loads on the structure. So when we applied the thermal loading on the structure, we find that these connection forces increased quite a bit, especially at the lower levels. So these loads were considered in the design of these connections.
And adding to this, Dr. Mehdi Yusuf, we also checked the maximum temperature we had in our column, and I believe that we didn't. There's a certain number, I don't remember off the top of my head, that if we don't exceed during fire, the column would go back to its original shape, so it won't be any elastic deformation. Maybe that's what you were concerned about. So we didn't pass the threshold for inelastic deformation, basically.
Yeah.
Okay.
Since it's study week, so we can take two more quick questions. I see in the chat there was a question. First question was to Mostafa Jr. about how was your transition from the Canadian code to the American code?
Okay, so I didn't have much experience in Canada. I did some private consulting with my professor, but I believe that the Canadian code and the American code are very similar. It's just a matter of maybe different factors. But we also have a recent hire who came from Canada, who was also from Western, in the geotech team, and he had no issues adapting from the Canadian code to the American code. They are very similar. It's a matter of knowing your basics.
And I mean, to add to that, our group is designing all over. So we just finished a project in Poland, and we had to get ourselves familiar with the European code. So we have to be flexible. And once you have your technical background is solid, you're going to be easily adapting from one code to the other.
Okay. Second question was, are there any big projects going on in Canada now?
Oh yeah, maybe you want to tell them about the REM project?
REM project, yeah. I mean, we have that big tunnel project in Montreal, and this it's huge. It's using a number of our engineers. We have like 5 of our engineers are working on this project, and it's in Montreal, and the Canadian offices are also working on it.
Okay, good. Another technical question, Mostafa. I see a lot of buckling analysis. Do you consider imperfections in all those analyses?
Consider what, sorry?
I see a lot of buckling analysis that you have done. Did you consider imperfections, geometric imperfection?
We did. So the way, as you know, that at least my buckling knowledge is limited. The way that we would get buckling in using software, because if you have a column that's perfectly with no imperfections, if you apply axial load, the software won't buckle. So the way we were introducing buckling is that we actually modify the geometry and provide slight imperfections at the start. So that's the way we initiated local.
The critical shape.
Yes.
Okay. Sounds good. Any other questions? I think that was.
I'll ask one more, Ashraf. So.
Okay.
Mostafa Elmorsi said that I shouldn't ask. I'll ask one more.
Okay. You guys, if somebody has any commitment, you can go now, because I know you might have commitments, and then we'll take Dr. Yusuf's question. Yeah.
So regarding the analysis for flexure and shear and torsion, I see that you did it in a stepped analysis. So you ignored the interaction between flexure and shear. And which is okay. It's acceptable by codes. I cannot deny it. But in reality, the flexure will affect the shear strength, and the shear demand will affect the flexural strength. It depends on the values, of course. So it's just a general comment. I know that the code doesn't address it, but it would have been good if you looked at the, it will have made your life more complicated, I know, but it's a point that you can consider in future.
Okay, thank you.
Okay, Moustafa, so you are having another master defense now. Okay, thank you very much all. Thank you for the speakers, Moustafa and Moustafa. It was an excellent presentation. And we hope that you keep hiring our good students. We have a lot of good students coming up.
Absolutely. Absolutely.
And thank you very much for your time.
Thanks for giving us the opportunity. Thanks.
Thank you, guys.
Bye.